Hello students, welcome to this new video presentation on thermodynamics part 2 which is given in chapter number 12 of physics for class 11. In today's presentation we will study about thermodynamic state variables and equation of state, thermodynamic processes, heat engines, refrigerators and heat pumps, second law of thermodynamics, reversible and irreversible processes, Carnot engine, and finally we will end this session by answering 1 mark and 2 mark questions from thermodynamics. Please listen to my lecture very carefully. This is very important and easy to understand, and note down all the important points. I welcome you once again. Thermodynamic state variables and equation of state. Every equilibrium state of a thermodynamic system is completely described by specific values of some variables like pressure, volume, temperature, and mass. A thermodynamic system is not always in equilibrium. For example, a gas allowed to expand freely against vacuum is not in equilibrium state. Please see the figure on the screen which shows the partition in box is suddenly removed, leading to a free expansion of gas, that is in figure A. In figure B, a mixture of gases undergoing explosive chemical reaction. In both the situation, the gas is not in equilibrium and cannot be described by state variables. Eventually, the gas attains a uniform temperature and pressure and comes to thermal and mechanical equilibrium with its surroundings. Thermodynamic state variables describe equilibrium states of system. The various state variables are not necessarily independent. The connection between the state variables is called equation of state. For example, an ideal gas, the equation of state is the relationship PV is equal to mu RT. This we have studied in the previous video also. For a fixed amount of gas, that is for a given value of mu, there are only two independent variables, say pressure and volume, or temperature and volume. The pressure volume curve of a fixed temperature is called isotherm. So iso means same and therm means temperature. So here temperature is constant, that is temperature is fixed. The real gases may have more complicated equations of state. The thermodynamic state variables are of two kinds, extensive and intensive. The extensive variables indicate the size of the system. The intensive variables are pressure and temperature, and they do not describe the size of the system. It is easily seen that the internal energy capital U, volume capital V, and total mass M are extensive variables. Pressure P, temperature T capital T, and density rho are intensive variables. It is good practice to check the consistency of thermodynamic equations using this classification of variables. For example, in equation delta Q is equal to delta U plus P into delta V, where Q is the quantity of heat supplied, delta U is the incremental increase in internal energy, and delta V is the change in volume. Quantities on both sides are extensive. Thermodynamic processes. Consider a gas in thermal and mechanical equilibrium with its surroundings. The pressure of gas in that case equals the external pressure, and its temperature is same as that of its surrounding. Suppose that the external pressure is suddenly reduced during the process. The gas passes through the states that are not in equilibrium. So, the non-equilibrium states do not have well-defined pressure and temperature. In the same way, if a finite temperature difference exists between the gas and its surroundings, there will be a rapid exchange of heat during which the gas will pass through non-equilibrium states. In due course, the gas will settle down to an equilibrium state with well-defined temperature and pressure equal to that of surroundings. The free expansion of gas in vacuum and a mixture of gases undergoing an explosive chemical reaction are also examples where the system goes through non-equilibrium states. Non-equilibrium states of system are difficult to deal with. It is therefore convenient to imagine an idealized process in which at every stage of the system is in equilibrium state. Such a process is in principle infinitely slow, hence the name quasi-static, that means nearly static process. So we will again describe a quasi-static process. A quasi-static process is an infinitely slow process in which the system changes its variables like pressure, volume and temperature so slowly such that it remains in thermal, mechanical and chemical equilibrium with its surroundings throughout. A quasi-static process is obviously a hypothetical construct. In practice, processes that are sufficiently slow and do not involve accelerated motion of piston, large temperature gradient, etc. are reasonably approximation to an ideal quasi-static process. We shall from now on deal with quasi-static processes only, except when stated otherwise. Isothermal process, a process in which the temperature of the system is kept fixed throughout, is called an isothermal process. The expansion of gas in a metallic cylinder placed in a large reservoir of a fixed temperature is an example of isothermal process. Heat transferred from reservoir to system does not materially affect the temperature of the reservoir because of its very large heat capacity. Isobaric pressure. The pressure is constant. Iso means same, bar means pressure. Isobaric means constant pressure. That is, pressure is constant. Isochoric processes. In isochoric processes, the volume is kept constant. It is just like a cooker, pressure cooker. The volume remains same, but as we supply the heat to the pressure cooker, the pressure changes but volume remains constant. Adiabatic process. If the system is insulated from the systems, that is, the cylinder or the container is totally isolated from its surroundings and no heat is allowed to go out of the system and to absorb the temperature or the heat from the surroundings, then the process is adiabatic. Adiabatic means heat is not allowed to enter or go out from the system, and no heat is supplied to the system, and such a system is called adiabatic process. The definitions of these processes are summarized in the table shown on the right hand side. Please see the table on the right hand side. Here the process, isothermal process, temperature is kept constant. The feature of isothermal process is temperature is kept constant. In isobar, pressure is kept constant. In isochoric process, volume is constant, and in adiabatic process, no heat flow, that is delta Q is equal to 0. And we will study all this in subsequent slides. First, we will take up isothermal process. For an isothermal process, that is temperature is fixed, the ideal gas equation is PV is equal to constant. That is, the pressure of a given mass of gas varies inversely. So P is inversely proportional to 1 over V, or P is proportional to 1 by V. This is nothing but Boyle's law. Suppose an ideal gas goes isothermally from its initial state P1, V1, T1 to a final state, then P to a final state is P2, V2, T1. So temperature, you see the temperature is in the previous case initial state also T1 and final state also T1, because there is no change in temperature. It is fixed. At any intermediate stage with pressure P and volume change from V to V plus delta V being small, the work relationship is delta W is equal to P into delta V, because delta Q is 0. So the equation becomes delta W is equal to P into delta V. That is, as the delta V tending to 0 and summing the quantity, delta W over the entire process can be written as W is equal to integral of V1 to V2 volume change of P into dV. And again rewriting the formula, P is equal to mu RT divided by V, we can get W is equal to mu RT into integral V1 to V2 of dV by V. Therefore, W, taking the integral, we get W is equal to mu RT, that is constant outside, natural log of, that is integral of dV by V is natural log to base E of V2 by V1. Let it be equation 1. So if we draw a graph between pressure and volume as shown in the figure, these are called PV curves or isothermal process. If we keep the temperature T1 constant, the curve will be like this, as shown in the figure. V is on x-axis and P is on y-axis. Similarly, if we plot the relationship W is equal to mu into RT into log to base E of V2 by V1, we will get a graph shown on the right hand side. That is the right hand side. Here V is horizontal, that is x-axis, and y-axis is P, and the plot is like this. That is, as we increase the volume, the pressure decreases. We have used ideal gas equation PV is equal to mu into RT. For an ideal gas, internal energy depends only on the temperature. Thus, there is no change in internal energy because we know internal energy is a function of temperature. There is no change in temperature, hence no change in internal energy, and ideal gas is an isothermal process. The first law of thermodynamics implies that the heat supplied to the gas equals the work done. So in the case of the first law of thermodynamics implied that Q is equal to W because internal energy is 0. Note for equation 1 here, as V2 is greater than V1, if V2 is greater than V1, W is greater than 0. And for V2 less than V1, W is less than 0. So work done is negative. That is, in an isothermal expansion, the gas absorbs heat and does the work. That means when the gas absorbs heat, then the system does the work. While in isothermal compression, work is done on the gas and heat is released. Adiabatic process. In adiabatic process, P changes, that is pressure P changes, volume V changes, and temperature T also changes. But the total heat supplied is 0. The heat is 0. Essential conditions for adiabatic process. To achieve the adiabatic process, all the walls of the container and the piston must be perfectly insulated. The speed of process should be fast. Example of some of the adiabatic processes. Sudden bursting of a tube of a bicycle is an example of adiabatic process. Propagation of sound waves in air and other gases. Now, to calculate the energy in adiabatic process, we have to take delta Q is equal to 0. Therefore, delta U plus delta W is equal to 0. Therefore, if delta W is positive, then delta U is negative because we are taking the second term on the right hand side. That is, adiabatic expansion produce cooling. If delta W is negative, that means here if delta W is negative, then delta U is positive. That is, the adiabatic compression produces heating. So it is the case of if delta W is negative, then it is a adiabatic compression. Equation of state. The equation of state for adiabatic process is PV to the power of gamma is constant. Let it be equation. Here P is pressure and V is volume. Gamma is a universal, is a constant of ratio Cp by Cv. This equation can also be written as substituting for P, Pv is equal to RT. We can write T into V to the power of gamma minus 1 equals constant, or T to the power of gamma divided by P to the power of gamma minus 1 is constant. So these are the three different forms of writing adiabatic process. Adiabatic curve. The PV graph, that is pressure versus volume graph, are called, in the case of an adiabatic curve, is called adiabatic curve. PV graphs are called adiabatic curve. And slope of this curve is given by the relation tan phi is equal to minus of gamma into P by V, where tan phi is the slope and gamma is the constant and P is pressure and V is the volume. The plot, a typical plot of P versus V, is shown in the figure. Please note the shape of the curve. Here, and the volume is plotted along the x-axis. Vi is the initial volume and Vf is the final volume. Pressure is on the vertical axis. So we can also calculate, please note the equations for work done in case of a adiabatic process. So it is given by W, work done is equal to P1 V1 Pi Vi minus Pf Vf. Pi is the initial pressure, Vi is the initial volume corresponding to this point, and Pf and Vf are given as shown in the figure, that is final pressure and final volume, divided by gamma minus 1, that is equal to mu into R. R is the universal gas constant of an ideal gas. Mu into R into Ti minus Tf divided by gamma minus 1. So derivation we will take up in the next slide. Now let us calculate the work done in a adiabatic process of an ideal gas. Let the adiabatic change of state take place from P1 V1 T1 to the state P2 V2 T2. Therefore, equation of state for an adiabatic process is given by P into V to the power of gamma is equal to constant. Let it be equation 1. So, to calculate the work done, we have to integrate. W is equal to integral V1 to V2 of P into dV. That is equal to P we know is equal to constant divided by V to the power of gamma. So that is, it can be written as equal to constant into integral dV by V to the power of gamma, because P is equal to constant by V to the power of gamma. That can be written as, taking integration from the knowledge of our integration, constant is V to the power of minus gamma plus 1 divided by 1 minus gamma for the limits V1 to V2. Substituting the upper and lower limit, we get constant divided by 1 minus gamma into 1 over V2. That is the first we have to put the upper limit V2 into to the power of gamma minus 1 minus 1 over V1 into gamma minus 1. But we know that P1 V1 to the power of gamma is equal to P2 V2 to the power of gamma is equal to constant for a adiabatic process. Substituting, we get the equation 1 over 1 minus gamma into P2 V2 to the power of gamma divided by V2 to the power of gamma minus 1. That is, the constant is substituted by P2 V2 to the power of gamma minus P1 V1 to the power of gamma divided by V1 into V1 to the power of gamma minus 1. Please write these steps one by one, step by step. You will understand it in a better way. Therefore, 1 minus gamma into, so rearranging V to the power of gamma and V2 to the power of gamma minus 1, we get P2 V2 minus P1 into V1. Therefore, we can write it as P2 V2 as mu r T1 or T2, mu r into T2 and mu r into T1, and rearranging the sign here 1 minus gamma and taking minus sign outside, we can rearrange and write it as mu r into T1 minus T2 divided by gamma minus 1. Please note gamma is the ratio of Cp over Cv. Let it be equation 3. So the graph for the work done is shown in the figure. Free expansion. The free expansion is a diabatic process in which no work is performed on the system or by the system. The final and initial energies are equal in free expansion. Isochoric, isobaric and cyclic process. Isochoric process. In an isochoric process, volume is constant. No work is done on the gas or by the gas. Hence, from the equation, that is the equation of first law of thermodynamics, delta Q is equal to delta U plus P into delta V. Because their volume is constant, delta V equals 0, and hence this second part on the right hand side is 0. Delta Q is equal to delta U. The heat absorbed by the gas goes entirely to change its internal energy and its temperature. The change in temperature for a given amount of heat is determined by the specific heat of the gas at constant volume. Isobaric process. Iso means same, bar means pressure. Isobar means same pressure. So P is constant. In an isobaric process, P is fixed, pressure is fixed. So work done is given by W is equal to P into V2 minus V1. So while there is change in volume, that can be written as mu R into T2 minus T1, because P into V2 is mu R into T2. Similarly, P into V1 is mu R into T1. Let it be equation 1. Since temperature changes, so does the internal energy. So both internal energy also changes. The heat absorbed goes partially to increase the internal energy and partly to do work. The change in temperature for a given amount of heat is determined by the specific heat of the gas at constant pressure. That is, here the specific heat is Cp, where pressure is fixed. Cyclic process and non-cyclic process. Please see the figure. The figure shows the cyclic process in a clockwise direction. So the state pressure changes from P1, it changes from A to B, B to C, C to D, and it comes back to A. So pressure changes from P1 to P2, remains constant, and then it changes from P2 to P1, and then the volume changes from V2 to V1. So in negative, that is anti-clockwise cycle, that is negative work is done. Here the changes take place from V1, that is A to B, B to C, C to D, and D to A. That is in anti-clockwise direction. A cyclic process consists of series of changes which return to the system back to its initial state. So it starts with A, goes to B, goes to C, D, and comes back to A state, initial state. In non-cyclic process, the series of changes involved do not return to the system back to initial state. That is, in non-cyclic process, the changes take place, but it does not come back to its initial state. That is, it does not come back to state A in case of non-cyclic process. In cyclic process, change in internal energy is zero because it comes back to its original position and temperature of the system remains constant. Heat supplied is equal to the work done by the system. For cyclic process, PV graph is a closed curve as shown in the figure above, and area enclosed by the closed path represents the work done. So A, B, C, D is a work done. This is a positive work done if it is a clockwise movement, and negative work done if it is an anti-clockwise direction. Please remember that. If the cycle is clockwise, work done is positive, and if the cycle is anti-clockwise, work done is negative. Heat engines. The basic features of a heat engine are schematically represented in the figure shown on the screen. Heat engine is a device by which the system is made to undergo a cyclic process to convert heat energy to work. In simple language, heat engine converts heat energy to work. It consists of a working substance, that is a system comprising of a working system. The working system can be a mixture of fuel vapor and air in a gasoline chamber, or a diesel engine, or it can be a steam in a steam engine. And the working substance goes through a cycle consisting of several processes. In some of these processes, it absorbs total amount of heat Q1 from the hot reservoir. This is the external hot reservoir. It absorbs heat energy, that is heat Q1 from the external reservoir at a temperature T1. In some other process of cycle, the working system releases a total amount of energy, heat Q2 to the cold reservoir, which is at temperature T2. Please note the hot reservoir temperature T1 is higher than the cold reservoir temperature T2. The work done W by the system in a cycle is transferred. So it absorbs heat from hot reservoir Q1 and delivers work to the environment via some arrangement. This working system may be in a cylinder with a moving piston that converts mechanical energy to the wheels of a vehicle via shaft. Say for example, in our motor vehicles, it can be an engine, car engine, IC engine, internal combustion energy. It generates heat and converts the heat energy to work. This cycle, that is absorbing heat energy from hot reservoir Q1, doing some work and delivering some heat energy to Q2 to cold reservoir, is repeated and again to get useful work for some purpose. The discipline of thermodynamics has its roots in the study of heat engines. A basic question relates to the heat efficiency of a heat engine. The efficiency eta of a heat engine is defined by eta is equal to W divided by Q1, where eta is the efficiency of the heat engine and W is the work done and Q1 is the quantity of heat absorbed. Q1 is the heat input and W is the work done. Q2 is the heat rejected to the environment, that is to the cold reservoir. Then, according to the first law of thermodynamics, over a complete cycle, W work done is equal to Q1 minus Q2. That is, eta efficiency is equal to 1 minus Q2 over Q1. For Q2 equal to 0, if Q2 equal to 0, then eta will be equal to 1. If it is 0, the engine will have 100% efficiency in converting heat into work. Note that the first law of thermodynamics, the energy conservation law, does not rule out such an engine. But experience shows that such an ideal engine with efficiency equal to 1 is never possible, even if we can eliminate various kinds of losses associated with actual and practical heat engines. It turns out that there is a fundamental limit of efficiency of heat engine set by an independent principle of nature called the second law of thermodynamics. The mechanism of conversion of heat into work varies for different heat engines. Basically, there are two ways. The system, that is a gas or a mixture of gases, is heated by an external furnace, as in the case of a steam engine, or it is heated internally by an exothermic chemical reaction as an internal combustion engine or IC engine. The various steps involved in a cycle also differ from one engine to another, which you will be studying in your higher classes. A refrigerator is a reverse of heat engine. Here, the working substance extracts heat Q2 from the cold reservoir at temperature T2. Some external work is done on it and the heat Q1 is released to the hot reservoir at temperature T1 as shown in the figure. Whereas a heat pump is the same as refrigerator. What term we use depends on the purpose of the device. If the purpose is to cool a portion of the space, like the inside of a chamber, and the higher temperature reservoir is surrounding, we call the device a refrigerator. Whereas if the idea is to pump heat into a portion of space, for example, a room in the building where outside environment is very cold, the device is called heat pump. The coefficient of performance alpha of a refrigerator is given by the relationship alpha is equal to Q2 divided by W. Let it be equation 1. Here Q2 is the heat extracted from the cold reservoir. See here Q2. And W is the work done on the system by the refrigerant. Whereas for heat pump, alpha is equal to Q1 by W. Note 1. The eta, the efficiency by definition can never exceed 1. Alpha can be greater than 1. Whereas you see the efficiency of the system can never exceed 1. Whereas the coefficient of performance alpha can be greater than 1. By energy conservation, the heat released to the reservoir is Q1 is equals W, that is work done, plus Q2. There are two inputs, so W plus Q2, and that is equal to Q1. Therefore, alpha is given by alpha is equal to Q2 divided by Q1 minus Q2. Let it be equation 3. In a heat engine, the heat cannot be fully converted into work. Likewise, a refrigerator cannot work without some external work done on the system. That is, the coefficient of performance in the equation 3 cannot be infinite. Second law of thermodynamics. The first law of thermodynamics is the principle of conservation of energy. Common experience shows that there are many conceivable processes that are perfectly allowed by the first law and yet are never observed. Clearly, some additional basic principle of nature forbids the above, even though it satisfies the energy conservation principle. The principle, which disallows many phenomena consistent with the first law of thermodynamics, is known as the second law of thermodynamics. The second law of thermodynamics gives a fundamental limitation to the efficiency of a heat engine and the coefficient of performance of a refrigerator. In simple terms, it says that efficiency of a heat engine can never be unity. According to the equation, eta efficiency equals 1 minus Q2 by Q1, which implies that heat released to the cold reservoir can never be made zero. For a refrigerator, the second law says the coefficient of performance can never be infinite. Accordingly, according to the equation, alpha is equal to Q2 by W, which implies that external work W can never be zero. The following statements, one due to Kelvin and Planck denying the possibility of a perfect heat engine and another due to Clausius denying the possibility of a perfect refrigerator or heat pump, are concise summary of these observations. So, the statements of second law of thermodynamics are Clausius statement. It states that it is impossible for a self-acting machine to transfer heat from colder body to hotter without the aid of external agency. The work done by external agency in this case is W. Kelvin's statement. Kelvin's statement says that it is impossible for a body or a system to perform continuous work by cooling it to the temperature lower than the temperature of the coldest one of its surroundings. Planck's statement. The Kelvin-Planck's statement says it is impossible to design an engine that extracts heat and fully utilizes into work without producing any effect. Reversible and irreversible processes. Reversible process. A reversible process is one which can be reversed in such a way that all changes occurring in the direct process are exactly repeated in the opposite order and in inverse sense. So, a reversible process is one which can be reversed in such a way that all changes occurring in the direct process are exactly repeated in the opposite and inverse sense. The conditions for reversibility are: there must be complete absence of dissipative forces like friction, viscosity, etc. should not be there in the for the reversible process. The speed of process should be infinitely slow. The temperature of the system must not differ appreciably from its surroundings. Examples of reversible processes are: A. All slow isothermal and adiabatic changes are reversible. Very slow evaporation or condensation is also a reversible process. Irreversible process. Any process which is not reversible exactly is an irreversible process. So, any process which is not reversible exactly is an irreversible process. Examples of irreversible processes: sudden expansion or contraction. It cannot be reversed. So suppose there is a sudden expansion somewhere, you cannot bring it back to the original position. Similarly, if something contracts, you cannot bring it to the original position. Heat transfer between bodies cannot be reversed. Carnot engine. In the year 1824, Sadi Carnot, a French engineer, first considered a question: what is the maximum efficiency possible for a heat engine operating between two reservoirs? And the next question was: what cycle of processes should be adopted to achieve the maximum efficiency? Interestingly, Carnot arrived at the correct answer, even though the basic concepts of heat and thermodynamics had yet to be firmly established in the year 1824. So, Carnot engine is designed as a theoretical engine. This engine cannot be realized in actual practice. To understand the design of Carnot engineering, we have to study the Carnot cycle shown on the screen. It is nothing but a PV diagram with different processes. The working substance of the engine undergoes a cycle known as Carnot cycle. So the design engine, Carnot engine, was following undergoes a cycle known as Carnot cycle, which is shown on the diagram. This cycle has four strokes or four steps. The first step is thermal expansion from point A to point B, wherein the states variables like P1, V1, T1 change to P2, V2, T1. The pressure, volume and temperature. Temperature is same at point A and point B. So this isothermal expansion from A to B, heat is added, but pressure and volume change from P1 V1 to P2 V2. Temperature remains constant at T1. This is isothermal expansion. The next step is adiabatic expansion from point B to point C, shown in the figure. Here, the pressure, volume and temperature change from P2 V2 T1 to P3 V3 T2 as shown in the figure. The temperature has changed from T1 to T2 and pressure from P2 to P3, volume from V2 to V3. The third step is isothermal compression. See, this is going in the opposite direction. It is compression where heat is ejected. A Q2 quantity of heat is ejected or rejected. So, the pressure, volume and temperature change from P3 V3 T2 to P4 V4 T2. That means T2 remains same because of isothermal compression. So, pressure and volume change from P3 to V3 from point C to point D shown in the PV diagram on the screen. The next and final step is from point D to point A, which is an adiabatic process. That is adiabatic compression. So here the pressure and volume as well as temperature change from P4 V4 T2 to P1 V1 T1. So this is completes one cycle A to B, B to C, C to D and D to A, and between A and B there is no change in temperature but heat is added Q1, that is work done is equal to Q1 minus Q2, and between point C and D iso Q2 is rejected and that is T2 to T2 only. Efficiency of Carnot cycle. The efficiency of Carnot cycle is given by the relationship eta is equal to 1 minus T2 by T1. Here the temperatures T1 and T2 are in Kelvin. Thus, the easiest equation shows the efficiency of a heat engine depends only on temperatures T2 and T1. Efficiency of a heat engine is always less than unity because T2 by T1 is a negative factor and it is less than 1. The whole of heat can never be converted into work, which is in accordance with the second law of thermodynamics. Then a Carnot theorem was established, which states that Carnot reversible engine working between two given temperature is considered to be the most efficient. With this, we come to the conclusion of chapter number 12. Now we will take up some worked examples. Very short questions of answers 1 mark. Why spark is produced when two substances are struck hard against each other? Work is converted into heat. Question number 2. What is the specific heat of a gas in isothermal process? The specific heat of a gas in isothermal process is infinite. Question number 3. On what factors does the efficiency of Carnot engine depends? Efficiency is given by the relation eta is equal to 1 minus T2 by T1. It depends entirely on the temperature of sink and the source. Question number 4. What are two essential features of Carnot's ideal heat engine? One is source and sink have infinite heat capacities. The second point is each process of engine cycle is fully reversible. Question number 5. Plot a graph between internal energy U and the temperature T of an ideal gas. Answer. Please see the figure here. The energy is on y-axis and T is temperature. So there is a direct relationship. It is a straight line starting from the origin. Refrigerator transfers heat from cold body to hot body. Does this violate the second law of thermodynamics? Answer: no. External work is done because on refrigerator external work is done. Hence, it does not violate the second law of thermodynamics. Question number 7. Is it possible to increase the temperature of gas without giving it heat? Yes, it is happens during adiabatic processes. During adiabatic process, there is no heat added to the system. Question number 8. Can the specific heat of a gas be infinity? Yes, it can be infinity. Question number 9. Out of the parameters temperature, pressure, work and volume, which parameter does not characterize the thermodynamic state of matter? Work. Temperature, pressure and volume are state variables. Work is does not characterize the thermodynamic state of matter. Question number 10. Why a gas is cooled when expanded? Decrease in internal energy. So the gas is cooled due to decrease in internal energy. Next question. Why does the air pressure in a car tire increases during driving? So we know that PV is equal to N into RT or mu into RT. Therefore V is constant, T increases. Therefore so also P also increases because P is directly proportional to T, temperature. As the temperature increases, volume is constant and P increases. P and T increases. Question number 12. Heat is supplied to a system but its internal energy does not increase. What is the process involved? It is isothermal expansion. Under what ideal condition the efficiency of Carnot engine be 100% if the temperature of sink is 0 Kelvin? Which thermodynamic variable is defined by the first law of thermodynamics? The first law of thermodynamics defines the internal energy. Question number 15. Is coefficient of performance of a refrigerator a constant quantity? No. As the inside temperature of the refrigerator decreases, its coefficient of performance decreases. Question number 16. What is the efficiency of Carnot engine working between ice point and steam point? So we have to substitute. At the ice point, the temperature is 0 degree centigrade Celsius, that is equal to 273 Kelvin. At the steam point, it is 100 degrees Celsius, that is 373. Substituting in the equation, eta is equal to 1 minus T2 by T1, we get efficiency as 26.8%. Question number 17. Heat cannot flow itself from a body at a lower temperature to a body at higher temperature is a statement or a consequent of which law of thermodynamics? See, this is stated in second law of thermodynamics. Question number 18. What is the specific heat of a gas in an adiabatic process? The specific heat of a gas in adiabatic process is 0. Next question. Heat system based on circulation of steam are more efficient in warming a building than those based on circulation of hot water. Why? Because steam at 100 degrees Celsius has more heat than water at 100 degrees Celsius. Write two limitations of first law of thermodynamics. First limitation is it does not give the direction of flow of heat. Second limitation is it does not explain why heat cannot be spontaneously converted into work. Question number 21. Write expression of CV and CP of a gas in terms of constants R, gamma, and where gamma is equal to Cp by Cv. Answer. We know given that gamma is equal to Cp by Cv and Cp minus Cv is equal to R. Therefore, Cp is equal to gamma into Cv. Therefore, gamma minus 1 into Cv. So, substituting, we get gamma minus 1 into Cv is equal to R. Therefore, Cv is equal to R divided by gamma minus 1 from the derivation. Therefore, Cp is equal to Y into Cv, that is R by gamma minus 1. Next question. No real engine can have an efficiency greater than that of a Carnot working between the same low temperature. Carnot engine working between the same low temperature. Why? Answer. In Carnot engine, there is absolutely no friction between wall of the cylinder and piston, and working substance is an ideal gas. In real engine, these conditions cannot be fulfilled. Question number 23. Why water at the base of waterfall is slightly warmer than at the top? Because potential energy is converted into kinetic energy. Some part of kinetic energy is converted into heat. Question number 24. When ice melts, the change in internal energy is greater than that of the heat supplied. Why? We know dq is equal to du plus dw. That dq is the change in heat is equal to change of internal energy plus change of work done. Therefore, du is equal to dq minus p into dv, because dw is p into dv. Give two statements of second law of thermodynamics. Clausius statement: it is impossible for a self-acting machine to transfer heat from a colder body to a hotter one without the aid of an external agency. So Kelvin's statement is: it is impossible for a body or a system to perform continuous work by cooling it to a temperature lower than the temperature of the coldest ones in the surrounding. Next question. An ideal monatomic gas is taken around the cycle ABCDA as shown. Calculate the work done during the cycle. Please see the diagram. It is given. So the difference is all 1p and volume is volume is 1 also. Change in P pressure is also 1. So hence the answer is P into V. Work done is P into V. Can a room be cooled by opening the door of a refrigerator in a closed room? No, it violates the second law. Question number 8. Explain what is meant by isothermal and adiabatic operations. Adiabatic process, pressure, volume and temperature of the system changes, but there is no exchange of heat. That is, no heat is given or transferred. In isothermal process, pressure, volume changes, temperature remains constant. Isothermal means, iso means same, thermal means temperature. Final question 29. Two bodies at different temperatures T1 and T2, if brought in thermal contact, do not necessarily settle to mean temperature. T is equal to T1 plus T2 by 2. Explain. So this explanation is given in step. Heat flows from higher temperature to lower temperature until the temperature becomes equal. Therefore, consider two bodies, M1 of mass A, body A with mass M1, specific heat C1 and temperature T1, and second body of mass M2, C2, specific heat C2 and temperature T2. T1 greater than T2, heat will be lost by A and gained by B. According to the principles of calorimetry, heat loss is equal to heat gain. Let the temperature attained be capital T. Therefore, equating the relation M1C1 minus M1C1 into T equals M2C2 into T minus T2. Therefore, M1C1T1 minus M1C1T equals M2C2T minus M2C2 into T2. Therefore, simplifying, we get the value of T as M1C1T1 plus M2C2T2 divided by M1C1 plus M2C2. It is possible only if M1 is equal to M2 is equal to M, C1 is equal to C2 is equal to C. Therefore, T is T1 plus T2 by 2. With this, we come to the conclusion of chapter Thermodynamics. Next, we will take up chapter number 13, that is kinetic theory. Till then, goodbye.